Hi guys, this is Rocky, Priyal, and Emmy, and we're going to be discussing feedback loops today. To begin, we're going to define a few key terms and go from there. Homeostasis is the tendency of an organism or cell to regulate its internal environment and maintain equilibrium, usually by a system of feedback controls so as to stabilize health and functioning. To maintain homeostasis, communication with the body is essential. The image below is an example of how a homeostatic control system works. Here is a brief explanation of it. A stimulus produces a change to a variable, which is the factor that's being regulated. A receptor detects the change, and the receptor monitors the environment and responds to change, which would be the stimuli. Input is the information that travels along the afferent pathway to the control center. The control center determines the appropriate response and course of action. Output is the information sent from the control center that travels down the efferent pathway to the effector. And the response is a response from the effector balances out the original stimulus to maintain homeostasis. Think of it as an extremely complex balancing act. Here's a few more definitions you may want to know. Afferent pathways, they carry nerve impulses into the central nervous system. For instance, if you felt scorching heat on your hand, the message would travel through different pathways to your central nervous system. Efferent pathways carry nerve impulses away from the central nervous system to effectors, which can be muscles or glands. The feeling of heat would travel through an efferent pathway to the central nervous system. It would then interact with the effector and travel down the efferent pathway, eventually making the person remove their hand from the scorching heat. We regulate our homeostasis through two major types of feedback mechanisms, positive and negative feedback loops.
There are key differences between these two types of mechanisms, but they still both revolve around one main idea: dealing with stimuli. Feedback loops consist of three parts: stimulus, control center, effectors. Both negative and positive feedback have these, but the effectors and control centers operate differently. A stimulus is something that disrupts homeostasis. Depending on what the stimulus is, we have built-in mechanisms to handle it. One of those mechanisms is negative feedback. Negative feedback is the most commonly used feedback loop in the body, and it is used to negate or counteract a stimulus without completely eradicating it. Negative feedback is a common mechanism in the endocrine system and elsewhere that maintains homeostasis. A good example is how the body maintains proper levels of thyroxine. When the level of thyroxine in the blood is too low, the hypothalamus stimulates the anterior pituitary to release a hormone, thyroid-stimulating hormone, which stimulates the thyroid to release more thyroxine. When the levels of thyroxine in the bloodstream is adequate again, the hypothalamus stops stimulating the pituitary. The control of the blood sugar glucose by insulin is another good example of negative feedback mechanism. When blood sugar rises, the receptors in the body sense a change. In turn, this control center, the pancreas, secretes insulin into the blood, effectively lowering blood sugar levels. Once blood sugar levels reach homeostasis, the pancreas stops releasing insulin. The thermostat attached to an air conditioner helps maintain a constant temperature in your house. During the summer, the sun heats the house and the temperature goes up. When the temperature goes up, the thermostat turns on the air conditioner, causing the house to cool down. When the house is cool again, the thermostat turns the air conditioner off. This is a negative feedback loop because temperature changes in the system are reduced. Another example is your internal body temperature needs to stay constant. When you exercise or go outside on a hot day, your temperature starts to increase. Your nervous system sends information to your brain about the change in temperature, and your brain in turn sends signals to your skin to tell you to sweat. The evaporation of the sweat helps keep your body cooler. When you quit exercising or go back indoors, your body cools back down to your normal temperature. Signals are again sent to your brain, and your temperature tells your skin to quit sweating. Again, this is a negative feedback loop because temperature changes in the system are reduced.
Go. Positive feedback has the same mechanisms, but they're used differently. One key difference is that positive feedback loops are used to eradicate a stimulus. Another key difference is that the responses through positive feedback become more amplified over time. So once a stimulus activates a positive feedback loop, it is not turned off until the stimulus is completely removed. Positive feedback loops and mechanisms tend to be more intense than negative feedback and can be life-threatening if they get out of control. Let's use a fever as an example here. A fever is caused by an invading organism, or the stimulus, such as a virus or a pathogen. There are certain cells in our blood and tissues that will begin to attack these pathogens and secrete chemicals called pyrogens to the brain. These pyrogens will then travel to the hypothalamus, which is the control center in the brain, which is where the core body temperature is regulated. These pyrogens trick the hypothalamus into thinking our core body temperature should be higher than 98.6 degrees Fahrenheit. So we will get cold at first and then start to shiver because our brain thinks our body temperature should be higher. Then we will feel very hot once we reach this new temperature. The brain will maintain the fever and high body temperature until the virus is completely eradicated. So as long as the virus is present, the cells will continue to secrete pyrogens and will also increase the rate at which it does this. If our body temperature climbs too high, then this can be threatening to our life and well-being. Positive feedback enhances an already existing response to complete something. During childbirth, for example, the pressure of the baby's head against the sensors near the opening of the uterus stimulate more uterine contraction, which causes increased pressure against the uterine opening, which causes yet more contractions. So this positive feedback loop brings labor to an end and the birth of a baby. One other example of positive feedback can also be seen in helper T cells in the human immune system. When a specific T cell is selected and activated by the MHC antigen complex, it proliferates and makes thousands of copies of itself called clones. And then these clones are then used to secrete cytokines, which further stimulate the cell activity. In this case, an army of helper T cells is produced to fight a specific antigen. When the invading antigen is destroyed, the helper T population is no longer needed. Only a small number of memory helper cells remain to circulate in the blood. This is very different from negative feedback. And just as a general example, let's say you get a rash from poison ivy. You know you shouldn't scratch it, but it itches, so you do scratch it. And then the scratching it making it itch more. And then that makes the rash spread to other areas that didn't itch before. And so you learn as the more you scratch, the more it itches. This is a positive feedback loop because a change in the amount of itching is promoted or increased. Positive feedback loops like this are often called vicious cycles. Let's say that a farmer has insect pests on his crops, so he sprays a pesticide to control the insects. After several seasons, the insects start showing resistance to the pesticide, so the farmer sprays even more pesticides and even more toxic pesticides. This further increases the selection pressure on the insects, and after a few more seasons, nothing seems to work against the pests. So the more the farmer sprays, the worse the problem becomes. This is a positive feedback loop because a change in pest proteins and pesticide resistance is promoted.